In this lesson, we are going to be looking at applications of electrostatics. We're going to be looking at something called a cathode ray tube. In this lesson, we are going to be looking at an application of electrostatics called the cathode ray tube, or the CRT. Cathode is a name for a negative. So this is also referred to as an electron ray tube, and is set up as follows. If I have a charged plate at a distance from another charged plate, and I charge this plate with electrons and this plate with a lack of electrons, I get a potential difference between these two plates. They both have a potential, but there's a difference between the two. And this one might have a negative 200 volt, this one might have a positive 500, in which case the difference is 700. And we can arbitrarily, since it's the difference we're going to be interested in this problem, we can always assign the value of 0 to the negative plate and give the full difference to the positive plate. So if I wanted to call this 700 volts, which I won't be making use of in this problem, but I can call it 700 if I had a negative 200 here and a 500 there. Or if this was a 200 and this was a 500, I could call this 300 volts and this one 0. So I will just set the one plate equal to 0 and the other equal to the total difference, because it's the difference I will be interested in making use of. Now, in order to cause the electrons to pop off of this plate in a particular location, we will apply heat at that point. So if I have an element here, which I run current through, again, it becomes hot at the end here. This heat heats up the molecules in here. They start bouncing around, and finally the electrons just start popping off of there. And this is where they're going to head, because in between these two plates we have a uniform field that's been generated because of the potential difference. Out of positive into negative is our field. It's uniform. Electrons will fly straight in that direction. Now, if we were to drill a hole in the opposite side, right across from the point here, when that electron does get kicked off this surface, there's a chance that it will fly straight through that hole on the opposite side. On its trip there, it will be changing its potential energy into kinetic energy, as we've looked at before. And we have that relationship where the work required to move that electron to this side is going to equal a change in kinetic energy. We also know that the work required is a negative change in potential energy. It's a negative amount of work because it wants to go there. So we end up having this relationship. I can now substitute from here what these values are going to be. Potential energy for a set of plates, you will recall, is the charge times the potential difference. I'm not going to plug in the number 700 at this point in time, but that's what the potential difference is, as I pointed out. And that's going to equal 1/2 mV final squared minus 1/2 mV initial squared. and this term is 0 since it started from rest. So now I have an equation where if I take the charge of the electron and plug it in here, it's a negative charge, and a negative of a negative becomes positive. So we have the negative of the elementary charge times the potential difference equals 1/2 mv final squared. And this describes the event taking place as the electron moves from this side to that side. And when the electron passes through that hole, it will have a velocity indicated through this equation. Now, because a cathode ray tube has more than just this one component, we will call this, or indicate that, through saying this is an accelerating voltage here. It accelerates the electron. So we'll put an A there, and this final velocity is due to that acceleration. So we're going to call that V final A. I'd like to show you a picture of a cathode ray tube. Here it is right here. Cathode ray tube is what is on the back of a television, or in the back of a television, CRT. So you'll notice, if you look at this picture, that we have the heating coil right here, or the point. It's near the cathode. If you want to have a better look at this, you'll find the same picture in your textbook on page 486. So this heating element heats up this cathode, which is the negative plate. The electrons hop off of that plate, moving towards the anode over here, which is a positive plate. We don't need to pay attention to the grid at this point. It doesn't change the mathematics or physics, as far as we're concerned, involved. The electron then passes through the hole in the positive plate, and it heads through deflecting plates. So now we're going to have to look at the mathematics involved in what happens during this deflection. Now we're just going to examine the horizontal plates here, or the vertical plates, because it causes vertical deflection. They're horizontal plates, but they're causing vertical deflection, so they're referred to as vertical deflection plates. So this will be a set of plates much like these two plates. There will be a cathode and an anode, and if we would like to, we could switch the current and cause those to switch roles. If this is a positively charged plate up here, then it will cause the electron, as it passes between those two plates, to be pulled towards that upper plate and pushed away from the bottom plate, thus changing its path. And if I add more voltage there, I can change its path more, and I can cause this electron to hit right at the top of this plate. I can make it so this variance in voltage will allow me to make the vertical alter all the way up to the top, or I can switch and make this a negative and this a positive plate, cause the electron to drop all the way down here. And a slow variance of those, I can cause it to, one after another, slowly place electrons all the way down the screen to the bottom. So now we're going to examine the physics involved in this plate here. We'll assume that we can make the extension to the horizontal deflecting plates, which will have a similar effect, but this time moving the electron left to right on the screen, or the television screen that we would be looking at. So we're going to ignore this one, and we'll just focus on this one and assume we understand that one after we have understood this one.